Hello, everyone. Welcome again. My name is Sebastian Martinez. I'm gonna be your guide through a bunch of exercises that we're gonna be uploading this semester to help you out to exercise some of the content for homeworks and also exams. Today, we're gonna work on problem 66 from the book, which is close to a homework problem. First of all, let's go through the problem. It says calculate the Thevenin equivalent, northern equivalent, and also the current flowing to some load specified there. So this is a very simple example, but it's going to help you out to exercise the calculations using complex numbers. First of all, I wanted to clarify something. The circuit given here is already on the phasor domain. So in general, there is an intermediate step or a first or step number 0 to get here, which would be to transform all these elements into impedances. Okay, it's assumed that all of these are ohms, and also it's assumed that this current source has a magnitude that it's an RMS value. That's the assumption that we're going to use throughout the course, which is normally you're going to have the variables in the time domain, and then when you transform into the phasor domain, then you use the RMS value. The impedances are calculated based on one particular frequency, which in this case is unknown because we already are on the phasor domain. So those things you have to take note to, and you have to be able to transform the circuit and its components from the time domain to the phasor domain and backwards. Okay, so let's go then to the solution. Thevenin equivalent. What is the Thevenin equivalent? Before calculating anything, let's try to draw or make a draft of our solution. We want to find out what would be a circuit on this form connected to the terminals AB. So essentially what we need to do is work with the elements that we have on the circuit to make it look like this. So when we do that, this is going to be the V Thevenin, and this is going to be the Thevenin impedance. Easy enough, playing with impedances. So one thing that I want to give you as a good practice here is that all of these elements now can be known as impedances, as boxes that can be combined in series or in parallel depending on the connection. So there's no more subdivision between resistor, inductor, and capacitor. They're all impedances in the time domain. So let's start with that. Let's start thinking of this circuit as boxes. So we have our circuit in the time domain. Of course, based on the value of the impedance, then we know that if we have a positive imaginary number, then this has to come from an inductor because of the definition, right? The Z of an inductor is J omega L. Omega is positive, L is positive, so the impedance related to an inductor is always positive. For a resistor, a pure resistor, we always gonna have only a real part that is positive also. And for capacitors, then it's always negative. Why? Because of the definition again. The C of the capacitor, it's 1 over j omega c, or we can see it as minus j over omega c. So omega and c are both positive, so we always gonna get something negative, right? A negative imaginary part in the impedance. So take that into account, and that is going to save you a lot of time and double checking. So now let's do something and let's combine these two in series. When we do that, then we get this circuit, and they combine in series, so we can think of two resistors in series kind of thing, which would be only the equivalent would be the sum. So we're gonna get a complex number, 12 minus J34. That would be the combination of those two elements into just one impedance that has real part and imaginary part. And again, the A, B are there. Then what we're going to do is to simply combine these two in parallel. And we're going to get one equivalent. A and B still have 22 angle 30. And the parallel here, I'm going to put it here, C equivalent, will be calculated as if you would have two resistors, right? So would be one impedance, so let's call it Z1 times Z2. Let's use the proper convention with the dot there, because we're talking about the complex number, and Z1 plus Z2, right? Taking into account, of course, that this is what we call Z1 and this one is what we call Z2. So the calculation in this case would be J10 times 12 minus J34 over J10 plus 12 minus J34, right? So this calculation can be done by hand, definitely, but I highly recommend you to use your calculator. Any of your calculators is designed to manage complex numbers, so you would have to go to the settings and see how would you input this kind of equation to be solved. In general, we're going to be talking about these complex numbers in rectangular form, meaning real and imaginary part. So A plus JB, that would be the rectangular form. Or the other way to talk about complex numbers, it's with a module and an angle. Just like the current source here, right? That's in rectangular form, but it's still a complex number. So my recommendation here in terms of calculation is that you go to the settings, go on a YouTube video that explain you how to use the complex number on your particular model of calculator, and this is going to save you a ton of time again. Learning to use your calculator for this type of calculations, it's essential for this class. You should be comfortable inputting this type of equations into your calculator and being able to solve it. So in this case, the result is 1.666 plus J 13.333. Okay, so that would be this equivalent impedance, 1.666 plus J 13.333. And without thinking about it, I think we got the northern equivalent. We got this one. That's already the northern equivalent, right? Uh, Northern equivalent is essentially a uh, current source connected with an impedance in parallel. And that's it. So this circuit, it's actually Norton equivalent, where this is what we call the Norton current, and this one would be what we call the Norton impedance. Again, the nomenclature here is that we use a dot on top of the variable when we're referring to the complex number. If we were using only in, we would be referring only to the module, to the magnitude of this phasor. Same with impedances. Impedances are always referred to the complete number. If we were using only Zn, then we would refer to the absolute value of this complex number. So we would have to calculate, right? A squared plus b squared, all of that in square root. That would be the amplitude of that impedance. We can see it as a complex number simply. So we're good with that one. Now the question is, let's go back to the Thevenin equivalent. We have the Norton equivalent. Let's put it out here. We have the Norton, sorry, this is in parallel. Norton equivalent, In, Zn. Let's use the same notation. I think Professor Pulgar uses a dot on top instead of a bar. It's depending on the book, actually. So the Thevenin equivalent would be simply a voltage source in series with an impedance, and based on what you know from classes and also from 201, you should be already familiar with this transformation, and you know that in this case the Thevenin equals the transformation of sources in this case. So it would be the Norton current times the Norton impedance, while the Thevenin impedance will be equal to the Norton impedance. So this is ready. The only thing that we need to do here is to calculate this this multiplication. So this would be 22 angle 30, which is the Norton current, this one, times this impedance. That impedance would be times then 1, how much is it? 1.6. 1.666 plus J, 13.333. Okay, and again, this is another type of calculation that you would do with your calculator. Two complex numbers, one in polar form, this is called the polar form, and another one in a rectangular form. Okay, that's what you need to input in your calculator and get the actual results. Again, this can be done manually, yes, but from now on my recommendation is to do it on your calculator. You're always going to have it available, and it's way easier. So when you do that, so let's get rid of this one, it's not in the way. You should get 488.68 angle 120 degrees. That's what you should get for the voltage BTH. And finally, the Thevenin impedance and the Norton impedance are the same, so we already have those values. Okay, great. Then the Thevenin equivalent will be simply this. Um, 1.66 plus J 13.33, and the voltage we said is 488.68, angle 120. Perfect. We have solved then part A and B. And again, we have used series, parallel, we have used transformation of sources, and the Thevenin and Norton equivalents. Now let's answer the last question. How do we calculate the current flowing from A to B if there is a 7 minus J2 ohm impedance connected across those terminals? So that means we're going to have, let's get rid of something here. We're going to have an impedance here, A and B. How much is it? 7 minus J2. So 7 minus J2. So one thing that you can notice already, if you want to go one layer down the analysis, this even though it's an equivalent impedance, we know that this comes from a resistor and inductor, an equivalent resistor and inductor, because we have a positive real part and a positive imaginary part. So the simplest equivalent circuit in the time domain has to come from a resistor and inductor. Here we have a positive real part and a negative imaginary part. So this one has to come from a resistor and a capacitor in series. Has to come from that. Whoops. So you already know, even though that we're working with phasors and impedances and everything are simply boxes here, the equivalent circuit in the time domain has to be something like what I just described. So let's go and calculate this current. Let's call it just I. In this case, let's use the same color. Will be the voltage source, right? So let's call it VTH divided by the sum of the two impedances, since they are in series, right? So we're going to have this voltage divided by the equivalent impedance, and that would be it. So let's call that Z Thevenin plus Z load. So that would be 488.68 angle 120 degrees divided by the total impedance here, 1.66 plus J 13.3 plus 7 minus J2. That's it. So we reach a point again when we need the calculator. And I'm going to read this message again. Feel comfortable using your calculator. We have a polar form on top. We have two rectangular form on the bottom. We can do those calculations by hand. Use your calculator. It's going to save you time. So if you do this, it should give you 34.25 angle 67.40 degrees. amps. This is amps, right? We're talking about phasors. So when we're referring this to amps, the real part, sorry, the magnitude of that phasor corresponds to the RMS value, definitely. We started with RMS, so everything is RMS. Voltages and currents are RMS values. Um, Impedances are in ohm, so they don't have actually RMS or maximum value. And I think that answers the question. Calculate the current. So, of course, given the flow of the problem, we calculated the equivalents and then we used them to answer this question. But most definitely, you could have just calculated this current if you wanted to. Go directly here, do some equivalence, series parallel, transformation of sources, and calculate this current. That's no problem. With the knowledge that you have on circuits, you should be able to solve the circuit however you want. Hmm? If the problem is specifically asking for something, just like Thevenin equivalent or Northern equivalent, which is an intermediate step to solve the problem, then you have to do it. But in general, the questions are going to be more open. Calculate this current, calculate this voltage. Uh, so you should be able to move the circuit around. And to summarize this, and I want to give a final recommendation, always on the phasor domain, think of this as impedances. They're all boxes that can be combined in series and parallel. Even though they may come from a more complicated circuit or from elements such as resistor, inductors, and capacitors, in the phasor domain, they're all boxes that can be combined. So that is going to save you a lot. Think of them as resistors. We kind of converted into an equivalent circuit similar to a DC circuit where we have only resistors, but in this case we have only impedances, right? And this approach of thinking about an AC circuit. It's gonna simplify everything that you do because you are already familiar and quite comfortable with DC circuits. So AC, even though it gets more complicated, the whole transformation into a phasor domain aims aims to simplify the analysis and simplify the calculations, getting to something quite similar to DC circuits. So that's the first problem. Thank you for watching.